Thanks very much today. Thanks for Claire and Matthew and everyone who've organised today, and I think we've all benefited from some great presentations. We've been working for the last 8 years with James Cook Uni. We've got a couple of the key biologists here today, Maria and Andy, to answer any detailed questions, but we're certainly keen to explain what we've been doing, some of the applications that we've put macro to, and then how that could translate into an option with the cane industry. What we've looked at with the algae is really trying to actually generate and use the algae to remediate water from a whole range of sources and then process that algae into a range of useful products. So we're looking at actually pulling the biomass out and getting a value out of it. So not only do we get a value for the industry that we work with, where we either clean the water or remove nutrients from that water, we generate large volumes of biomass and we actually put that biomass to good use. The algae in the case of some projects is harvested daily, in the case of other projects it's every 2 to 3 days, and then some on a weekly basis, and that really depends on the quantities of nutrients coming through. But the further you refine the algae, the greater the levels of value, and I guess we've spent the last 6 or 7 years making sure that our systems grow algae efficiently. We've been able to substantially improve productivities. We've been able to operate with different seasonal flows of nutrients, and really this has given us a great basis on which to get in and look at some of these other uses for the process. We've really focused on algae that's very robust. We need algae that will span different salinities, different applications, and we've honed in on a couple of key algae that grow well up in the Brisbane region. They're products that we've worked with for the last 3 or 4 years, and we've really spent a lot of time understanding the value there. So robust growth and continuous growth is very important as a basis for getting consistent results with that water remediation. It needs to be a product that we can grow year round. We do look at some seasonal applications of different forms, and here we look at ulva in a blade form, which grows well for 8 to 9 months of the year. In fact, we've grown it through the full year, but in the summer when temperatures rise and salinities change, we look at a filamentous version, and each has really good properties and each has really good values to be gained. And what we've done is we've applied it largely with aquaculture. We've also looked at other saltwater sources, but really taken the nutrient-rich water out of fish and prawn farms, looked at that water and made sure that we reduce it to a level lower than the intake water for the farm, and then look at the uses that we can take out of the algae. At the moment we're operating and cleaning about 1 meg per day per HRAP, and that then generates sufficient biomass to go into organic fertilisers. But as we get larger quantities of the algae, we're looking at some of these higher value extracts, and so the guys have been doing a lot of work with pulling those olivins out of the ulva, and they're a really high value soluble fibre that has ready markets, and again each of the areas need to have existing markets so you can get that value out of the algae as you pull it out of the water. With freshwater, and really unique to James Cook Uni and these processes, is Oedogonium. The culturing and growing of Oedogonium has been really put to good work in each of the projects. Andy's had a project at Kelso where they took freshwater barramundi and the nutrients coming out of the freshwater barramundi and cleaned that water up, and more recently for the last 18 months we've had a project there at Cleveland Bay, and again Andy's been pulling that together and making sure that year round we understand performance. We needed to know that in Oedogonium we had a robust species. We've grown Oedogonium in a range of different climates. We've grown it up in China. We always source a local strain with ice on the paddle wheel in winter and up to 40 degrees in summer, and we've had obviously less variance up there at Cleveland Bay. So again, we take water, we grow the algae in the water, and then we look at a range of uses and values that come out of that algae. So in the case of Cleveland Bay, in the case of the local Oedogonium, we're getting 20 to 25% protein. We're getting reasonable levels of omegas, so there's good applications in extracting those valuable elements, and then looking at using the residual as a a combination with the biosolids at sewage farm to create energy and more fertiliser. So again, we look at every part of the value chain and look at making sure that there's really good applications for the product that we have. In doing this over a range of time, we've got a really clear understanding of how the algae goes, the growth rates, the levels of sunlight and the temperature of the water, the flow rates of the nutrients, really all of the aspects that come together to make sure that the project has good, efficient operation through the year, and that we can adjust the flow rates and other characteristics in the operation to make sure we're getting that optimum growth and that optimum levels of water treatment. But the nice thing is it's very robust and strong through the year. So in taking the knowledge of how to grow algae, in taking the knowledge of what valuable products we can pull out of that algae, we've really put that to good work at a number of projects, and we've spent the last 4 years working at Pacific Reef Fisheries. It's one of the largest prawn farms in Australia. It generates levels of nitrogen and phosphorus. They're required to, for a new permit, which is the first permit in 15 years, prove that the system that's in place can deliver full reduction to the water, to take out all that nitrogen and phosphorus that's put in by the prawns or the fish, and to remove that so they can either recycle the water or discharge that water. And in doing the trials over the last 3 years at PO site, and there's a video on our website which we haven't got time for today, but if anyone wishes to have a look, it's quite a good one. It gives you a clearer indication and understanding than my description. But we've been able to come up with a really good proposition for other farms to expand and double their production. So at at Coral Coast Barramundi, Australian prawn farms and Pacific Reef Fisheries, we're really providing good projects which enable them to improve their production and raise additional product for sale, and we're able to get some valuable algae that comes into good financial outcomes for MBD. This has sort of seen a number of compliance projects where farmers are producing more nitrogen and phosphorus than their existing permits allow, so they can either reduce their production or they can put a system like this in, pay us about 3 to 5% of their revenue, so it's a small percentage of cost. We've based all of our remediation charges on $30 a kilo for nitrogen, and we obviously make most of our money out of algae size. We've then seen a number of really good potentials for reef protection. I'll get on and explain a number of those projects going forward. We've really tried to focus on those projects where we see great potential, and this photo is an interesting one here in that the area of the prawn farm that you see with water is about 70% of the prawn farm, 70 hectares, and the farmer's been able to operate at that farm and grow prawns in that area and still meet his environmental discharge limits. The whole area in grey he wasn't able to farm with until we came up with a system that cleaned the water and enabled him to use that full farm. So he's been able to increase his production by 30% at this site and still live within the discharge limits that have been granted. All new permits don't provide those legacy discharges and require to remove, so there's no impact to environment. So we set up a range of parameters and we really monitored the system within each of its life over 3 years, collected a lot of data, and we were able to demonstrate the system worked year in, year out, day in, day out. Through the course of the trial, we started looking at 1 turnover of water per day, and we in fact increased that substantially to where we were able to get up to 7 exchanges, but more typically about 3 or 4 exchanges per day. So it's been a great success as a project, but really enabled us to look further afield. And this slide goes to the economics just to give a quick understanding of why it's a good, cheap system for the farmer to operate. Every 50 kilos of prawns the farmer grows generate 1 kilogram of nitrogen. Off that 50 kilos of prawns, the farmer sells them for $20 a kilo, so he generates $1,000. He then pays MBD $30 to take 1 kilo of nitrogen, and we generate another $130 of value in the algae that we produce off that kilo of nitrogen. The farmer's happy, he's got a good low-cost system. We're happy because we've got a good, profitable operation, and the two fit hand in hand and enable this industry to substantially increase. And this slide goes to how the nitrogen through the system operates. We have water drawn and measured in terms of its background nitrogen levels. We talk a lot about nitrogen here, but it includes the take-up of phosphorus and other elements, generally in a 1:10 ratio, but Cleveland Bay, which we'll talk about at the end, in a 1:6 ratio because there's a lot more phosphorus in the water. That water's taken into the prawn farm. The fish and prawn provided with clean water and regular exchanges. The water then goes through an intermediate estuary, and then from there it travels through into the sand filter. The sand filter converts any organic nitrogen into inorganic nitrogen. Very efficient system with microbes, and takes advantage of a really well-designed system to get about in the mid-90s in terms of percentages of conversion. And then the water's pumped directly into our H-traps, and the H-traps then strip out that nitrogen, phosphorus and other nutrients so that the water comes back down below its intake levels, and that really creates a full system for water treatment there at the prawn. I guess the key thing here is that we're able to achieve zero impact to the environment. We're able to have an industry that's sustainable and can grow, and we're able to make sure that the water that travels out to the Great Barrier Reef is actually clean and fit for putting back into the environment. One of the interesting things with the expansion of this project is we'll look at 90% recycling of the water. So we've done a lot of work to test the water that we've cleaned in this process, and it's actually a perfect source for growing the fish and prawns. So really the intake water from the reef at Guthalunga will be used for top-up and salinity control. So it's a far lower demand than was originally envisaged when the expansion permits were originally granted. So having Garoompa, the Great Barrier Reef Marine Park Authority, approve the system through last year for expansion at the Guthalunga site has led to substantial interest from overseas. So the industry in Australia is small by world standards. The largest operators in Vietnam and Thailand have really rushed to look at the system. They've had a collapse because in their areas water quality hasn't been controlled. They've been able to discharge over many years and see water nutrients just rise and rise to a point where it's really damaged their production. In Thailand in 2012, 700,000 tonnes of prawns were produced. 2 years later, 200,000 tonnes were produced, and a loss of about $4 or $5 billion of income to the country. It's a very serious issue, but really with these systems we can clean the water on the way in, recycle it and keep it clean and keep that water much higher quality so that we can have better outcomes for the prawns. Thailand and Vietnam, we're seeing these projects move into being. The first project will actually be built in Vietnam before the end of the year, and then we'll expand with what you see there and move into Thailand in 2017. On to Great Barrier Reef protection programs. We think that the existing farms, there's great opportunity there to go back into the large operators and say, well look, the legacy permits that have been granted to you, if we provide the infrastructure and we deliver systems that can be retrofitted to your plants, would as an industry you be interested in reducing those levels? And we've had good support from the industry there. In terms of cane farm runoff, we think that the Ootagonian provides a fantastic opportunity, and we've got a bit more detail on how that would work in looking at a trial that would build on a report that BIFMAC prepared last year, and we've picked one of those farms as an example to develop. And finally, for the last 18 months we've been working at Cleveland Bay, and we've got the basis for a large-scale expansion there. So I think there's some really exciting uses for the algae and really exciting outcomes for each of these projects to go forward. The aquaculture cleanup is pretty obvious. It's using the existing levels of nitrogen and phosphorus. Each of these farms has to set aside 30% of its land area to clean water up. We can use about 10%, a third of that area, to clean the farm water up and then enable the farmer to get in and use another 20%. So it immediately releases more productive land, and we can stick within the discharges and clean that water up. With the cane farm runoff, it's a very significant contributor of nitrogen, phosphorus and other nutrients to the reef. And again, we've devised a system that we think has great and wide application, good low-cost system that brings us to what that looks like. The BIFMAC report identified 4 potential projects, and we've picked one that we're quite happy for anyone to have a copy of the slides, that really brings together a 900 hectare catchment. It really looks at all of the characteristics in terms of the water collection, the point at which would be optimal to put the system in. On 900 hectares we would need about 3.5 hectares of hay-traps, about 0.3% of the total farm area. We're using an area which is marshy and low value to the cane farmer, and we've also added a sand filter in there to clean up any organic nitrogen that comes through the systems. It's a matter of looking catchment by catchment for these systems and how they be best applied, but generally it's downstream. We can combine in with other systems, so we can combine in at the start or end of a wetland system, or we can simply draw off from existing water flows. We've really tried to come up with a system which, in terms of looking at the level of protection that you're providing for these storm events, we think that a relative level is about a 1 in 10 year protection. So 99.9% of storm events will be catered for, but the very large 1 in 100 year event for storms would simply bypass the systems and go back to that collection. Any system that's bored in, and in trying to set up collections and protection at 1 in 100 years, would require very, very significant infrastructure collection areas where we can put in place in the existing catchments a 1 in 10 year protection and really make sure that we treat that water in an ongoing basis. So it's about getting a level of protection that's applicable and suitable, and deciding, really letting the state decide where they wish to have that level. So it takes the runoff from the farm and that catchment area. It sets up 3.5 hectare trial, and the result is weekly collection of the algae and nice clean water to actually be reused or discharged straight out into the reef. I've explained that the sand filter really is important for collecting some of the fines, and really the level to which we wish to collect the fines will be dictated by what treatments on top of this we place. So we'll use geomesh and other filtration to really strip out some of those fines. We can even put because we can concentrate the water, we can actually put a filtration system at the back end to really get into very low size particulates. It looks at the level of protection we wish to address, and we're recommending 1 to 10 year protection there. It looks at the specifics of the farm and the location, the sand filter in yellow and the hay traps in green, the harvest system being placed at the end of those hay traps. Really looks at a system which has got a cost of about $1 to $1.5 million to establish, but then has more than a 20-year life and has great application at catchments through the system. So it's a matter of really looking at the other solutions that we've seen today, looking at this system and really coming up with the integrated approach for the reef. It's looking at reducing nitrogen and fertiliser loads at the front end and combining with the collection of runoff waters at the back end to get a suitable solution. These are just some of the layout configurations that we envisage would be applied, and it really depends on whether there are existing wetlands, where the available land is, and how we wish to treat that water going through. And look, I'll quickly just go through the other project up there, which is Cleveland Bay, and what we've done there over the last 18 months is really grown the algae and stripped the majority of nitrogen and phosphorus at the back end. This facility has to reprocess up 30% of its water, and so we're able to, at the back end, strip that phosphorus out in particular and enable them to have a one pass-through, and this is a project that's being expanded to initially 4 or 5 hectares, then 20 hectares, and with a bioreactor to start pulling out some of those higher value components, and then pushing out to about 200 hectares over the next 5 years to get full clean-up of the back-end water. Thank you.